Okay, so last time I talked about how in order to define a gradient, you need an inner product. All right, so that way if you have a scalar function of a vector, the gradient is defined, basically the derivative has to be a linear function that takes a vector in and gives you a scalar out. So this turns out this has to be, if you have a dot product, this has to be a dot product of something with the x, thing we call the gradient. So the gradient is the thing with the same shape as x that we take the dot product with the x to get df. So what I didn't mention is that in fact, not only do we need a dot product to define a gradient, actually we swept something under the rug earlier. We actually need a norm in order to even define a derivative in the first place. Right? So a norm, right, is if you have a vector space, a norm is some measure of the length, right, of the vector, or a measure of distance. So a norm takes in a vector v and gives you out a scalar. And technically, to qualify as a norm, it has to be, this map has to be non-negative. It can't be negative. It can only be 0 if v is 0. If you multiply the vector by 2, it has to multiply the length by 2. Or if you multiply the length by -2, it has to multiply the length by 2, or basically absolute value of any scalar. It has to satisfy something called a triangle inequality. So usually, most commonly, we're going to get a norm just from an inner product. So once you define an inner product, and we talked about those last time, you can even define inner products of matrices, you get a norm for free. You can take the norm, it's just the square root of the inner product with itself, and this satisfies all these properties for any inner product. So the reason I mention this, oh, and by the way, just cultural note, so if you have a continuous vector space with an inner product, that's a Hilbert space. If you have a continuous vector space with a norm, that's called a Banach space. So, it's a fancy sounding name, but it just means you have a norm.
You can impress your friends with your fancy mathematics, but that's all it is.
Yes. So the reason I wanted to mention this is that really the definition of the derivative that we used earlier implicitly requires us to have a norm. So it actually is of both the input and the output. So it really only applies to Banach spaces. So the reason for that is, remember I defined the derivative to start with is if you look at the change in the output, f of x plus delta x minus f of x for not an infinitesimal, but a finite delta x, but maybe small. Remember we defined the derivative as the linear part, is the linear operator that gives the change to first order, which means we dropped any term we called it little o of delta x, any term that goes to 0 faster than delta x, right? So any term that's small compared to this, right? But in order to define what it means to be small, you need a norm. Like how if I have two vectors, a column vector, and I want to say, is this column vector smaller than that column vector? How do I check it? I check the length, right? That you need to map it to a real number to get a distance or a smallness, right? So formally, the definition of this little o dx is basically any function such that the norm of this over the norm of delta x goes to 0 as delta x goes to 0. In fact, even to define a limit, you need a norm of delta x, because if you've taken the A to 100, there's this epsilon delta meaning of a norm of a limit. Sorry, so it's like you can make this arbitrarily small for you can make this less than or equal to epsilon for all epsilon greater than 0. I'm not going to go through the definition. If you've seen the definition of a limit, there's some absolute values in there that for vector spaces have to turn into norms. But basically,
my experience is everyone's seen the definition of delta and epsilon limits, and no one really understands it. Is that fair? Maybe some of you guys really do, but most of us don't.
Yeah, I mean, to be fair, it took people 2,000 years to figure it out, right? They really, the concept of a limit and an infinitesimal was a big struggle in mathematics, going back to these, the ancient Greeks, Zeno's paradoxes and so forth, right? So it really took a long time for people to nail down what this meant. But yeah, so you need to be able to have a length, a norm of the output, because this has the same, shape as the output. These are the same shape as f, right? To say that these terms are small compared to delta x, which you also need a norm of delta x, right? So just implicitly, you always need a norm of all of these things to define it. And usually we're going to get it because we're going to define, in most cases, we'll define an inner product. Because we'll want that anyway, because if we want to take derivatives of scalar functions, we want to be able to write down gradients. But this is what you really need. So anyways, I just wanted to this is something we swept under the rug in the beginning. But since we defined Hilbert spaces, and so I thought I should define a Banach space. I mean, I'm still sweeping some things under the rug, like I'm sweeping what does it mean for it to be continuous under the rug, but yeah, I wanted to throw that out there. That's all I wanted to say.
That's it?
Yep, any questions about that?
Questions? By all means. Okay, good. All right. So this is just a little notebook, and if we really need, this isn't the live version, so I can't really do anything. But I have a feeling that this will be good enough. But if we need the live version, we can just press a few buttons. So if I understood correctly, last time you got the answer for what is the gradient of the determinant? Is that right? Did you derive this formula that it?
I did not derive it. I just gave the answer.
You gave the answer, and there's a few different formats. Did you?
I gave it the first one, determinant A times A inverse transpose. Yeah.
Oh, the gradient is the determinant of A times A. That's the second one, right? So the first one is the cofactor of A, which is one of those linear algebra terms that you may or may not remember. This is the one, and just another term is the adjugate of A transpose, which is the adjugate of a matrix is the inverse of the matrix divided by the determinant. So
multiplied by the determinant.
Multiplied by the determinant, right? So it's so let's see, and of course, if you have the gradient, then did you write down this version as well? Last time, the D of the determinant?
No, well, I did D of any matrix function. So yes, it's that I defined the dot product, matrix dot product. So
right. I see. So D of the determinant will be the trace of whatever formula you have over here, this formula, right, times dA.
Transposed times it, yeah.
Yes, right, sorry. Let me clear my head. Yes, the trace of this thing transposed times dA, right, that which is the element-wise, it's just like the dot product. You all get that. It's just like the vector dot product. You multiply corresponding elements and you take the sum. Whenever you have the trace of A transpose B, as Stephen is writing very nicely over here, that's the A dot B. So if we know the gradient, then the D has to be this formula, okay? And I'm just defining the adjugate right here so that I can have it handy. As Stephen was saying, it's just the determinant times the inverse. This is just a definition. And then there's the cofactor matrix, which is the adjugate of A transpose. So I'm just using this. Once I've defined this one, to define this one, I just get to do the equality, right? So this defines these functions, and here I've sort of written it every which way. The inverse in terms of the adjugate and the cofactor, the adjugate in terms of the determinant, the inverse and the cofactor. Well, you get it. All three possibilities are written here. Okay, so for 2 by 2 matrices, here's the 2 by 2 matrix, and here's the cofactor matrix. Some of you will recognize that when you form the inverse of a 2 by 2 matrix, the determinant goes in the denominator, and the thing that goes in the numerator. Right, you're all good at 2 by 2 inverses. Do you know that by heart? Like, would you be able to do it in your sleep? Right, you switch the A and the D, and you negate the B and the C. Well, no. Let's see. You negate the B and the C, but I'm also doing the transpose. Right. So here it's right. So you negate the B and C and transpose because it's the cofactor. Okay. For the adjugate, you just take the minus. And anyway, these are all the formulas. Here's the inverse. Right, so the inverse is the adjugate divided by the determinant. Okay, doing all this numerically just for fun. So numerically, here's a random matrix and here's a random perturbation. What we're going to do is look at the determinant of the perturbed A minus the determinant of A. Right, so there's the numerical value. And by the way, I know Stephen has recommended always using things on the order of square root of epsilon to make the perturbations 10 to the minus 8th. And he's right. I never do that, but you should listen to him. I just start typing 3 or 4 zeros in a 1, And actually, it's been good enough for my purposes, just to check things. I mean, Stevens is more, it's the best possible one, a square root of epsilon. But with a quick and dirty test, I don't have the time to type all those zeros, and I never remember to type 1e minus 8. So I just type these 4 or 5 zeros, or 3, 4, 5 zeros. But in any event, here's what the finite difference. Here's the trace of the adjugate times. We see that they're correct to enough digits to believe it.
How come the adjugate is not transposed there? There's something missing here. It should be. Oh no, it's the adjugate. Yeah, okay, right. The determinant is the transpose of the adjugate. Never mind. So this is the great adjugate is the great.
I have to go back and look at these formulas to answer your
It's
question.
the transpose of the gradient, right? So yes.
Oh, because because it's right. Let me say it. Yes, what you just said, that the adjugate of the transpose is the thing that you want, and so the trace needs to transpose it twice, so it's left non-transposed. Yeah, you got it. The gradient is the one transposed, and this has to be the transpose of the gradient.
Yeah, this is gradient of determinant.
Right, like a double negative makes a positive, a double transpose makes for a no-op.
This is our dot product.
Yep, that's right. Okay. So to actually see the gradient, we can rely on Julia's internal forward difference mode, for example, which is forward differentiation. It's not forward difference. It's automatic differentiation. It's different from forward differencing. It's the forward mode automatic. I see this and I think forward differences, but it's not. And I think in this lecture, if I get a chance, just a little bit, I'll tell you about how this forward mode works. Stephen kind of gave you one view of it. I'll give you another view today. But you just say, give me the derivative or the gradient of the determinant function, and Julia will happily do it. And of course, I could compare that with the adjugate of A transpose. And you guys know me by now. When I see these things matching, it looks like to all the digits, it makes me happy. It makes me think, wow, this formula for the derivative is correct, right? So this for sure is the derivative of the gradient. Okay. I don't know. Maybe I tried to say this before, but I'm just going to repeat it if you've heard me say it. But just philosophically, I find it remarkable that you could think of a limit of a finite difference, and like the great mathematical gods let us have a formula for. I mean, you've all done it in calculus, like the difference of you take a sine and a little bit more sine, you get a cosine, right? Or, the log, you get 1 over x, or x squared, you get 2x. But like, I don't know. Could you guys imagine a universe where like the mathematical gods weren't kind enough that like not every integral could be written as a formula, right? I mean, that, as you know, lots of integrals can't be written in terms of elementary functions. But derivatives you could always do it, right? And you could do it for scalar calculus. That's why calculus is so easy to teach and is a beginning subject. You could do it for vector calculus, and you could do it for these complicated matrix functions. I don't know. Do you ever stop and think about that being remarkable, or you just take it as a given and move on with your lives? I think it's amazing that we could have a formula for this difference. I just do. And a simple formula, in effect. But maybe you guys just take it as a granted given. But I don't know. I think formulas are gifts from the gods, and I don't take them for granted. All right. So this is really just to show you how to do reverse mode in Julia. So it's not much different. I'm just calling Zygote, which is one of the big popular packages in Julia to do reverse mode auto diff. And you see it's not much different. This is the forward diff package dot gradient, and this is the Zygote dot gradient. And under the hood, it's getting the answer in a completely different way by going reverse mode, but it actually gives the same answer. Okay. Though I wouldn't be surprised, maybe Stephen knows better, I wouldn't be surprised if this is just built-in formulas in both cases. I don't know. Let's see. We could do it symbolically, but let's get to the proof. So there are a couple of ways to prove this mathematically. So one relatively simple proof is to remember the Laplace expansion of a determinant. So I suspect you all remember that if you want to calculate the determinant of a big matrix, Usually people take maybe the first row, but in fact you could take any row. But do you remember you take the top left entry times the determinant of the, what happens if you cross out the first row and first column, then the second entry and you cross out that row and column with a minus sign, plus minus plus minus. You remember that rule? So that's the Laplace expansion. And the key fact is that if, for example, if I'm working with AI1, let's say I'm starting with the ith row, then AI1 is not inside any of these C's, right? It's AI1 only appears here, right? Everything else you see depends on other elements of the matrix, but it doesn't depend on AI1, right? Similarly, if you look at AI2, CI2 and every other term only depends on AI2. And just to make that point very clear, here what I did was I took this matrix and I made this matrix, this 3 by 3 matrix, you'll see it's almost completely numerical, but I put one symbol in the bottom right, okay? And if you take the determinant, right, you see that this is an, I don't know whether to call this a linear or an affine function.
If you affine,
Affine for this class, some people would actually say it's linear in the sense of linear quadratic cubic, right? It's first degree polynomial. But let's call it affine for the purposes of this class because it's not 13a plus 0. But whatever it is, it's a first degree polynomial, right, is what it is. And the fact of the matter is the coefficient of a is exactly this determinant. It's the one that, it's 4 times 4 minus 3, right? It's 16 minus 3, it's 13, right? And so the coefficient of every, if you make any symbol, any element a symbol, the coefficient that's in front of it is just this minor, right? And so taking derivatives of first degree functions is easy. It's just the slope, right? The derivative of this determinant with respect to this element is clearly the number 13, right? And so the way to say this in general is if I want to take the derivative of the determinant with respect to any aij element, the slope is the thing that multiplies it. So it's cij, okay? And so that is one immediate way to conclude that the gradient of the determinant is the cofactor matrix. It's that simple. Okay? There's another proof that is sort of, this is more, I mean, this proof is pretty simple. I think it's easy to agree that this is a nice, simple proof. There's another proof that might seem slightly harder in one way, but in a way it's sort of, mathematicians like this kind of proof. And so, you get to take your pick which one you like best, but let me just show you an alternative proof. So in this alternative proof, what we're going to do is we're going to figure out the right answer near the identity, and then we're going to, use that to bootstrap ourselves to any other matrix. Okay? So if you know how to expand, like, you're all familiar, if I ask you to compute the characteristic polynomial of a matrix, let's call it M. Right? If I need to do the here, I'll do what Stephen does, and I'll do it like this. So if anybody asked you to calculate the characteristic polynomial, and I'm using the mouse, which means that it's really sloppy. Not that my handwriting's so great, but it's not this bad. All right. So the characteristic polynomial of any matrix M is usually written like this, right? And there's lots of factors. There's lambda to the n, and all the way down to the determinant, plus or minus the determinant of M, right? So you remember that, right? And if you want, you can if you want, you can make this a plus sign, and then you get all plus signs in this whole formula, right? And so this is not much different. Here, if lambda was 1, if you just took lambda equals 1, right, you'd have determinant of I plus, well, here, let's just see it this way. Determinant of I plus a matrix, right, would be 1 plus, right, and then there'd be the terms that you get, there'd be the next terms, right? This thing here, as you all know, is the trace of the matrix, right? So maybe I should have put that in. You get lambda to the n plus lambda to the n minus 1 times the trace of the matrix, right? So if you make a tiny little perturbation, the determinant of I plus dA, I guess I should have made this 1 plus the trace of dA, to be honest. Let's fix that right now, right? So the determinant of I plus dA would be 1, that would be like 1 to the n, plus 1 to the n minus 1 times the trace of the matrix, right? And then they're the lower order terms, right? So, so that's one way to think of it. And so there we immediately get, the answer around the identity. And now if we want to get this anywhere, all we have to do is recognize that if we want to go the determinant of A plus dA, then we just go A times A inverse over here. That's just the identity. But then we can use the properties of determinants to pull out the determinant of A, and you just get I plus A inverse dA, right? And so and this basically here we just think of this A inverse dA as the trace formula, right? And therefore we get our answer, right? The very answer we're looking for. In a way, this is more complicated, but mathematicians like this one better than, I don't know why. They're both valid. You get to take your pick. There's something I like about this, though. It is a little bit more complicated. Okay, but in any event, we get the same answer. Okay, so what do we have here? So application to the derivative of the characteristic polynomial. So once again, there's the simple proof. The characteristic polynomial of a matrix is the product of x minus the eigenvalues. Probably a different sign from what I had here. You take the derivative of this product. You get the sum of these products n minus 1 at a time, which you could rewrite like this. But you can also directly do, with our technology, you can do this and get basically the same answer as the direct proof. Okay, and then I have some numerical checks. Let's see, and the derivative of the log determinant. Log determinant comes up a lot. Logs of lots of functions come up a lot. For example, Stephen, about, I don't know, a few lectures ago talked about this f over f prime. It's what shows up whenever you do anybody's Newton's method, right? And of course, this could be written as 1 over the log f prime, right? So basically the logarithmic derivative and its reciprocal come up all over mathematics. So the derivative of the log of the determinant is simply the trace of the inverse times the dA. Okay, this you've seen, A inverse, and that's it. Okay. Any questions? That basically covers the gradient of the determinants. Any questions about that? So maybe a few words about determinant. Interestingly enough, people often tell you that you should never compute a determinant, or hardly ever might be a fair term. So determinants are real, it's a real favorite of elementary linear algebra classes. Right? Determinants are great for telling you in exact arithmetic whether a matrix is singular or not. Right? So a matrix has determinant 0, it's singular. If the determinant is not 0, it's not. And and that sounds like a really good idea to have something like that. But it turns out that when you're doing computations in finite precision, if you're doing it on a computer, the determinant turns out to be not so meaningful. It gets to be hard to compute accurately. There are a lot of issues with calculating the determinant. It turns out that while the pure mathematicians live in a binary world where a matrix is singular or non-singular, the truth of the matter is that the world of matrices is not so binary. It's a bit more of a spectrum where matrices are singular or nearly singular or a little bit bad or not, or not at all bad. And probably you've all heard the word that I'm referring to. It's the word that we use in numerical analysis is conditioning. So ill-conditioned means a matrix is nearly singular, right? And well-conditioned means that it's very non-singular, right? It's too many double negatives there, but it's sort of the good side of singular, right? When we say it's well-conditioned. Right, and so, the determinant doesn't really give. The determinant's not a really give a good job of talking about how nearly singular matrices are. The condition number, which is related to singular values, I'm not going to talk about that today, is a much better way of talking about matrices being singular or not. So. You learned it all in a course like 1806 or elementary linear algebra. You learned about determinants. And then later on, when you compute, people tell you to forget about determinants, right? Mostly. There are times, but mostly. Okay, so that, And the other thing we tell people to do is forget about the characteristic polynomial as well. That's not how we calculate eigenvalues either. We don't take roots of polynomials. Anybody happen to know how we compute eigenvalues in the real world? We don't do characteristic polynomials. Anybody know the magic 2 letters that happen when you type eigenvalues? How many of you just thought it was the characteristic polynomial? You take the roots. How many of you had any idea how roots got taken on eigenvalues got taken on a computer? So you have any idea what the algorithm is being used? The power method? Okay, so you probably didn't hear the student saying that, well, in 1806, I learned about something like the power method, which gives you the dominant eigenvalue. Yeah, so, and then nobody else in the room has any idea how eigenvalues get calculated? Just a little bit of culture here. So, people don't know. I see. I kind of felt like I ruined the question then. I should have just asked, how are eigenvalues computed? Because I imagine many of you would have said, isn't it the characteristic polynomial? You get the roots? Because every one of you have formed the characteristic polynomials of 2 by 2 matrices, and I know you have, right? You got that quadratic equation, and you solve for the roots. I know, you remember? Who remembers doing that? Right? Quadratics, you get the roots. You know, if you had a mean teacher, maybe they forced you to do a cubic, but I bet they didn't. Anyone ever do it for a cubic? Maybe it was rigged to be easy, though. You know, so none of that happens on the computer. I'm not going to tell you in detail how it's done, but I will mention just the fact that it's not the characteristic polynomial is half of what I want you to know, and the other half is there's something called the QR algorithm for eigenvalues. So in general, a QR for a matrix factors a matrix to orthogonal times upper triangular. And a funny thing happens if you factor a matrix into QR and then reverse it and get RQ. And if you do that again, factor that new matrix into QR and reverse it to RQ, and you keep doing that, essentially the eigenvalues magically appear. Right? And there are some details. If the matrix is symmetric, the matrix will actually become more and more diagonal as you go. If it's non-symmetric, but has real eigenvalues, it'll become triangular, and you'll see the eigenvalues on the diagonal eventually. And if it's complex, you'll get these little 2 by 2 pieces, which are easy to get the eigenvalues from. So there are a bunch of tricks to accelerate all this, but the basic idea is QR, RQ, QR, RQ. You might actually try it in Julia or Python or whatever, MATLAB, whatever you like to do one day. You'll see it just works.
But it is related to the power method under the hood, if you dig deep.
Oh, dig really deep. That's right. It's sort of like a block power method in multiple dimensions all at once. It's crazy. Yeah. Okay. All right. So that's that one.